Assalamu alaikum everyone. So lecture number 31, and today we will be talking about software defined radios. So before starting, let me talk about some sort of motivations regarding software defined radios. So whenever we think about the communication or think about the devices that are available nowadays within the market, so you can see on your screen we have a lot of different standards, a lot of different technologies. You can see quad band GSM, GPS. I want that my cellular phone should be able to provide GPS services. I also want that my cell phone should be capable of using Bluetooth technology, and moreover I want that my system, my cellular phone should be providing GPR services, edge services, and it should be supporting higher data rates that are provided by LTE. So I want to converge all those services into a single handset. So how is it possible, right? And then if we talk about the emergency situation, so most of the time when we have the situation or condition where we need the first line of communication at maximum, so we saw that the first line of communication mostly fails during emergency situations, whether it's flood situation, it's earthquake, or maybe some sort of other situation, hurricane or some other situation, right? So the first line of communication fails, right? And we are not able to build the infrastructure even in weeks, months, right? So this is the second point, that we need something else. We need software defined radios. And then let's talk about the frequency allocation, right? So here is the frequency allocation chart, right? And this is the frequency allocation used by United States, right? And you can see the complexity, right? So, and remember that this is very, very precious resource. If this resource is not being used efficiently, then the nation, the country, they have to bear great loss, right? So effective and efficient frequency allocation and frequency use. I'm not talking about the reuse, I'm talking about the allocation. So being the user, I always have the dream to have access any service anywhere over any technology. For example, if I am in my office, I should be able to access the services which I have. And if I'm moving on a public spot, or maybe I'm traveling in a car, or maybe moving in a bus or train, so I should be capable, I should be able to access different technologies, right? So different services over different technologies, any service, anytime, over any technology, right? And if I'm talking about this era of high data rate communication, where we are assuming that we are in the most advanced communication system era, right? So believe me that at this point in time, we don't have a single universal handset that is going to support most of the technologies, most of the standards. So every company has its own standard, right? If we talk about different carriers, they are adopting their own proprietary standards, and if we talk about some other carriers in other part of the world, they are trying to build their own way of building, developing, and doing their research, right? So we don't have a single universal handset at this point in time. And if we talk about this, this is all from the perspective of the end user. If we talk about the service provider, right? So if I'm a businessman, I have a company and I'm providing a service, right? So you can say I'm a carrier, and so I own an infrastructure. So I want that my infrastructure should be capable of providing any other standards that are being updated, upgraded, or maybe new standards. So this is from the carrier point of view, right? So the base station manufacturers, right, they want that their products, they are capable of supporting most of the services, because then they can attract most of the carriers. So this is another point that we can see that we have different antennas, different interfaces, different radio equipment, and we have to support different communication links, right? So how is it possible, right? And then if we talk about from the operator point of view, right? So if we have 6 operators within Pakistan, so every operator is trying to offer their own package, right, in order to attract the user. Some operators, carriers, they are targeting the users which normally communicate or which normally use their services at night. Some are targeting the business community, other ones are targeting the student community. So they have their own business objectives, right? And they have to change their business objectives very frequently. So how is it possible that they are able to launch different packages, different services, and it should be done very frequently and very fastly? Because if, let me give you an example. So within Pakistan, we don't have 3G communication, right? Officially, we don't have 3G communication, and government is now government has to outsource the frequency resource, right, or licenses for 3G. But if we talk about the carriers, if you go back 1 or 1.5 years back, right, so most of the carriers, they don't have this support for 3G services. Now what they did, they have swapped their equipment physically, and now they have installed, or they have put flexible equipment, so that if tomorrow, or maybe after 1 year, 6 months, or after some time, they have to support some more advanced services, for example LTE. So most of the carriers, they are in a position to support that. But you know that this is the flexibility, this is the power which I want you to motivate in order to have, right? So the network operators, they are very keen to offer services very quickly, very efficiently, in order to grab the business from the market, in order to grab the market, right? And if we talk about the space communication, right? So if I have launched a spacecraft maybe 10 years before, and I have the ground station for communication with that spacecraft, so I want to support newer protocols with the older ones, because the satellite was launched in 10 years before, maybe 5 years before. So this is another problem, right? So how I can do that? How I can bring this flexibility, that it should be backward compatibility, there should be backward compatibility when we talk about the space, deep space communication, right? So because the ground station, it has the flexibility, it has the provision to update the equipment, the hardware, the protocols, the communication system, but we cannot go into space frequently, right, to update the space station. So I want that the older protocols should be supported alongside the newer protocols, right? So this is another motivational point. Then if we talk about the subscribers, services, and developers, right? So we have international roaming problem, because if I have a connection over here, I am using a service over here for data, for voice, for some others, maybe triple play services. So if I have to go abroad, so I will be charged more, right? So there are some roaming issues, right? Then increase personalization, right, and choices. So I want that whenever I'm moving abroad, so my roaming profile, my personal information should not be shared, right? And then we require more flexibility into the services. For example, if I'm making a phone call by using my cell phone, and after some time the other party want me to start the video communication, so I should be able to convert to the video communication seamlessly, right? And obviously when we talk about services, so different services, they are actually developed or designed on the basis of different service logic, right? So nowadays the services are being developed very fastly and frequently, and there are services that actually are the mix of the basic services, voice, video, data, right? And then we want to have the unified communication. Any service, anywhere, over any technology, right, at any time. So we want unification. We want convergence of services onto a single platform. So if I'm associated with a carrier, so I want that my carrier should be providing all the services available at a single platform. So that is another requirement. And then standardization. So another issue is standardization. So whenever we talk about the communication, so as mentioned again and again, that this communication or data communication is a complex task. So we have divided that task into subtasks, and in order to perform those subtasks at different layers, we have to define different rules, bunch of rules, set of rules, right? So all the rules or the bunch of rules, they actually are protocols. So at different layers, we have different tasks that has to be performed under the control of certain set of protocols. So we have application, presentation, session, transport, network, data link, and this is a familiar and very renowned 7-layer OZ model. And this is a very generalized way of defining the data communication between devices, either fixed or maybe wired or wireless. Now, if we talk about the wireless communication, so again we have some layered approach over here: physical layer, MAC layer, and logical link layer. So all the wireless and wired communication has to be done by using certain standardized set of protocols, which is not the case again. So this is another issue, right? And moreover, we have certain regulation issues. For example, for one country we have to follow some rules A, and for other countries we have to follow certain set of standards of rules, for example B. And this is also a very different situation when in this global world where the communication is playing a very vital role for every aspect of life, from business, for medical, for education, right? So it's very difficult to have communication, to launch services, to launch different technologies, different protocols. So this is another problem when we talk about the software-defined radios requirement. So before talking about the silicon capability or computational power, let me give you an example. I have a system, and that is the system specifically designed for MPEG encoding, decoding, right? So within that system, what I will be having, I will be having specific application-specific processors, application-specific memories, right, and application-specific algorithms. So all is hard-coded. So if I'm sharp enough, right, so I will be able to maybe have support for 2 protocols, maybe at maximum 3 protocols, but again we have certain limitations. But if I want to design a flexible system, right, so that I want to get rid of this hardware-based system, or I want to encode all the filters, all the modulators, all the algorithms that are actually being developed within the hardware by using specific ASICs, by using specific hardware. So I can have a system, right? I can design, or I can have a software that can perform all the required functionality. But what is the requirement, right? So the requirement is that we should have a very fast computational, right? So nowadays, if we talk about a single personal computer, right? So we have quad-core processors, right? And we have memory in gigaspeed memories. So conventionally or typically systems are having high-speed memories, and the bottleneck over here is the data read and write from the hard disk, which is compensated by the solid-state disk. So now there is a trade-off, right? So of course we will not be having the same performance, same efficiency which we got by using the hardware-based MPEG encoder decoder, but you know that if I encode that onto my personal computer and I'm performing the same functionality of MPEG decoder encoder, then I can have great flexibility, right? So there is a trade-off, right, between the computational power and the flexibility and the performance, right? So when we talk about the wireless communication industry, so there are very frequent and fast evolutions. So if we talk about the link layer technologies, right, so you can imagine the evolutions that are being made during the last 20 and 30 years, right? So we have first G, 2G, 3G, and now we are in 4G, or we are expecting 5G, right, in a few amount of time. So you can see that there is an existence of incompatible wireless network technologies in different countries. So as a result, the deployment of different services that has to support roaming, they are not being deployed easily, right? So there are problems, of course, whenever we talk about a service. So the carriers, they want that the services should be available. If we talk about the developers, if we talk about different carriers, if we talk about different service providers, so they want that all their products should be used, right, everywhere, right? So this is a hindering factor for. So all these factors, all these points which I made subsequently, right, so they actually are leading us towards the development, deployment, and study of software-defined radio, right? So let's talk about software-defined radio, and we are not going to define what a software-defined radio is, right? So the objective of this talk, this lecture, is that the concepts, the technologies, the ideas, right, the protocols, the standards, and different concepts which we have studied so far, right? So we will be trying to use those different concepts, ideas, techniques, and technologies in order to grab this new technology, that is the software-defined radio, right? So software-defined radio is a system where the components that have been typically implemented in hardware. For example, when we talk about a communication system, so we have a transmitter, we have a channel encoder, right? We have source encoder, channel encoder, then we have a channel, so then we have in between antenna, channel, and then we have antenna, right? And demodulator, channel demodulator, and then decoding sort of facility, right? So all those different blocks, they involve different filters, different mixers, different amplifiers, modulators, demodulators. But remember, when we talk about the communication system, all the those different components, they are rigid, they are hard coded. You just can change, you just have very low flexibility in order to change that. For example, if I'm using a particular modulation scheme, right, for my system, so I have to stick with that particular modulation scheme. So if my system can amplify a signal to a certain extent, right, so I have to limitize it, right? So I have to be within the limits, right? And if we talk about the mixers, right, so we have again upper bound, or we have again limitations, right? So what software defined does provide us, right? It provide us the flexibility to code those mixers, those filters, those amplifiers, modulators and demodulators by coding at the software level on a personal computer. So we can use a conventional computational power or personal computational power, right, as opposed to the embedded system that is specifically designed keeping in view a certain communication system. So what is the advantage? So if I want to change the modulation scheme, I want to change the filter, right, I want to change the encoding decoding scheme, so I have the flexibility to do that, right? So the development of generic radio platforms that can be reconfigured on the fly, right, possibly by means of over-the-air downloads to target multiple radio standards operating over a wide range of carrier frequencies. So if I want that I have a radio, I want to change the frequencies over which it is transmitting and receiving on the fly, or in the battlefield, or maybe on the run, right? So this is not possible if we have a rigid radio. This is possible if we have a flexible radio, and the flexible radio is the software-defined radio. So we have different vision when we talk about the SDR. Whatever type of communication is required, wherever you are, either you are in the battlefield, or maybe you are traveling, or maybe we are in an emergency situation, and whenever you need it, right? So whenever you need it, so it's the vision of the SDR, software-defined radio, that, for example, let me give you an example, that we have an emergency situation where our underlying communication infrastructure, it is destroyed, and we want to rebuild new infrastructure, or maybe we want to repair that existing infrastructure. So in case of earthquake, this is not feasible, this is not possible. In case of flood, even we cannot repair it 100%. Maybe some part is repairable and some part is not repairable. Again, we cannot have communication. So what we can do, so we can build our own infrastructure, right? If we have this capability of deploying this software-defined radio, right, and we can have communication in this emergency situation, right? And we can have another example. For example, we are in the battlefield, and our enemy, it has trapped our communication, it has trapped our frequency. Though there are a lot of different mechanisms that we have studied so far. For example, we can use frequency hopping, we can use direct sequence spread spectrum, but even in that case, we can face certain problems, right? So what we can do, we can change our frequency, right? So this is only possible if our system have the flexibility to do that, right? So here we have different types of software-defined radios, tier, name, and features. hardware radio, baseline radio with fixed functionality. So we have fixed functionality that can be performed by this hardware radio. Then software controlled radio. The radio's signal path is implemented using application specific hardware. Signal path is essentially fixed. Software interface may allow certain parameters, transmission power, frequency, to be changed in software. So we have limited flexibility over here. And then we have second tier, software defined radio. Much of the waveforms, for example, frequency, modulation, demodulation, security, etc. is performed in software, right? So signal path with reason be configured in software without requiring any hardware modification. So here we need some sort of hardware modification maybe, and then we have the ideal software defined radio. Standard SDR and ISR implements much more of the signal path in the digital domain, right? And then we have ultimate software defined radio, USR, represents the blue sky vision of SDR, fully programmable traffic and control information. So here you can see that we have these tiers and the software part. So this is the antenna, that is the front end, right, between the system and the free space. And here we have the radio, and this radio is performing modulation, demodulation, security, and we have signal processing algorithms, right, or specific hardware that is actually performing signal processing, right? So if you talk about SCR, right, here is the HR hardware radio. So you can see we have very little software part. And we talk about SCR, you can see the software part is increasing, right? So here, so we are actually trying to move close to the antenna as possible as we can by grabbing all the functions, or by coding all those functionalities into the software, into the computer, right? So we are moving as close as possible near to the antenna. So here you can see we are very close to the antenna, very near to the antenna, that is transmission or receiving antenna, right? So capable of covering substantial frequency range, of executing software to provide variety of modulation techniques, wideband or narrowband operation, communications, security functions, and meet waveforms. Okay. So of course there are drivers, there are key players, right? And they are actually from academia, industry, and research, right? But there are a lot of different challenges, there are a lot of different problems, right? So as we know that the challenges, the problems, they brought opportunities with them, right? So they this is an opportunity, right? So the manufacturers, we talked about different manufacturers. For those are manufacturing hardware for carriers, base stations, and cellular phones, services, developers, operators, regulators, right? And standardized bodies. They are actually all are drivers, or they can push the software defined radio, right, all together. So this academia, industry, and research triangle, they should be benefiting from each other, right? So because there should be a linkage between academia and research and industry, right? So we have a lot of different efforts that are being made and that are continuing. For example, GNU radio, that is again an open source software defined radio, and this tool is developed by Virginia Tech University, that is again based on software defined radio concepts, OSSIE. And then we have a FunCube dongle, that is USB dongle, and we can have receive only communication infrastructure by using this solution. Then RTL dongle, and we have different forums where you can put your queries, questions, and you can learn a lot regarding software defined radio. And we have another company that is actually providing platform, that is the ATIS research, and they are providing USRP kits in order to have in order to support software defined radio. So one of the key driver of this software defined radio is the wireless internet, right? So cellular industry, wide area coverage, we wish global roaming, mobile users at great speed, subscription based right, license bands, right? And if we talk about the wireless LAN industry, local coverage, we want local coverage, no handoff or roaming, fixed users, and revenues through equipment sales, unlicensed bands, right? So this is one of the key driver for software defined radio, right? So if we talk about future communication trends, when we take into account software defined radio, right, or flexibility, so you can see that here we have the data rate and here we have the mobility, right? So as you can see, the data rate in 2G, and this is 2000, and then the data rate in 210, and enormous rise in data rate. And as we move on, right, so you can imagine the data rate in around 220. It's 622 mega, enormous. And even you can download a movie, right, within seconds, right? So the objective over here is high data rate, high mobility, mobility management, and system roaming, seamless connection to broadband services, right? So we want higher data rate alongside the mobility. So this is the key issue, key point, and this is the ultimate target. So let's have the block diagram of a digital radio system. So we have the information source, and this is the source encoder, encryption if we want security, channel encoder, modulator, and this is the RF front end. And those functions has to be performed in reverse order. Demodulator, right, detector, channel decoder, decryptor, source decoder, and this is the information sink, information source. And here we have the block diagram, right? So now you can see different sections. So we have divided this digital radio system into different sections. This is the RF section, right, where we have the antenna and receiver, transmitter, right? So this is a transceiver, and this is the if section, A to D converter, digital down converter, in for when we are receiving data. So when we are sending data, so digital up converter, right? And we have DAC, digital to analog converter, and this is the baseband section where we have to perform different DSP specific processing, and we have a FPGA, GPP, general purpose processors, right? So if we talk about the handset evolution, right? So you can see we have the blocks for different performing different functionality for a cell phone, for a handset, RF front end, analog if, A to D converter, D to A converter, and this is the baseband modem. And here we have the software part, right? And you can see that we have a very little software part over here, and here you can see that we actually are increasing the software part, right? So you can imagine here. So now we have 3 blocks within the software part. So it means those different functionalities are being encoded. So it means we are going towards more flexibility. So here, if we talk about again the software part, so it's on rising again, right? So here are some of the benefits of SDR. So ease of design, we can reuse right, the existing system. For example, if my system, communication system, is providing or supporting, or at present it is supporting or it is capable of handling certain modulation scheme. So what I can do, I can change the code, right? I will set certain parameters, so then I will be able to have support for some other modulation schemes, right? So in this way we can say that we have ease of designing a communication system. We can have easy realization of the communication system. And manufacturing, if we talk about the manufacturing, digital hardware reduces costs associated with manufacturing and testing radios, right? So if we talk about the SDR, right, so actually we can reduce the cost significantly, right? So if we compare the cost, although there is a trade-off between performance, but as mentioned that nowadays we have very high sort of personal computational power that can be used in order to have intensive communication that is required in order to launch different programs that are related to the SDR. Then we can have multi-mode operation, SR, change modes of loading appropriate software into memory, and we can use advanced signal processing techniques. And then of course there are few discrete components, implement functions such as synchronizations, and we can have the flexibility to add extra functionality, right? So if I have a communication system and I want to add some functionality, so what I can do if I have a hardware-based communication system, so maybe I have different slots to plug some cards, so this is the only flexibility I can have. But again, maybe I have to update the firmware, or maybe I have to change physically some cables, some connectors, and some other maybe antenna also. So but if we have the software-defined radio, right, so what we can have, we have the flexibility to add additional functionality onto the system, right? And there are some of the advantages. Flexible, right? Of course we have flexibility, power, and we can reconfigure again and again, right? And even we can change the firmware, right? Reduced obsolescence, multi-band, multi-mode, ubiquitous connectivity, enhances facilities experimentation. So we can have a platform. For example, if I'm doing some work on some protocol evaluation, link layer protocol evaluation, so I can have a platform, right, with flexibility where I can change different parameters, I can change different encoding schemes, decoding schemes, and then maybe error correcting schemes, or maybe channel modeling, right? So I can do a lot of different experimentation by using this SDR flexibility. And it actually, SDR is bringing the analog and digital world together, right? So we have full convergence. So we talk about the environment, it's analog, right? If we talk about the computer, where we have implemented most of our modulators, demodulators, filters, so this is actually digital. So we are actually converging, or bringing close together both analog and the digital worlds. Okay, so here we have facilitators for SDR antennas. So we need wideband antennas so that we can support, we are able to support a lot of different techniques, technologies onto a single system. Then waveforms, analog to digital converter. Of course we need high speed analog to digital and digital to analog converters. So actually that is the bottleneck. When we talk about the bottleneck, or we compare the hardware based DSP specific chips with the underlying SDR technology, so this is one of the bottleneck, right? So we need high speed A to D and D to A converters, and then we need to support, we need to have digital signal processing algorithms that should be facilitating SDR, amplifiers, right? So of course we need amplifiers, batteries, and cognition behavior and design tools, right? So these are some of the issues regarding SDR, right? And here are the projects that GNU Radio, that is a software defined radio, open source, OSSIE, OpenBSC, right? USRP. This is again a front end, right? And we have Osmocom SDR, and lastly Cisco and OpenFlow and OpenStack, they have defined software defined network, right? So this is again you can say a software based hardware, as in similar way we have the software defined radio, so we have software defined hardware or software defined networking, right? So we already know that when we talk about the communication specifically from the networking point of view, so we have two different planes, control plane and data plane, right? So what we will be doing over here while defining software defined networking, we will be separating control and data planes, right? So let me first define to networking that allows centralized programmable control, right? So that network operators can control and manage directly their own virtualized networks, right? So here is the big picture. So this is the conventional scenario where you can have, we have tight coupling of data plane and control plane, right? So distributed control of equipment, client server, the control plane and the data plane, they are tightly coupled, and you can see the distributed control of equipment, signal network physically, right? And if we talk about the software defined networking, so here you can see that we have isolated the control plane from the data plane, right? So separation of data plane and the control plane. Now you can see that we can have physically one network, but virtually we can divide the network into different segments. So here you can see we have the mobility support, we have the routing support, and here we have the energy efficient forwarding, right? So you can see the control has been detached, right? So it is centralized over here, and now we have a single point of control when we talk about the software defined networking, right? So here in this second part we will be talking about the software defined radio specifically. So here if we talk about the ideal software defined radio, we have an antenna, right? And then we have A to D converter, and this is the software subsystem. So this is the reception part. If we talk about the transmission, so here we have digital to analog converter because we are transmitting, right? Software subsystem, and this is the transmitter. Now this is the typical SDR, right? So you can see radio front end, and then we have receive signal path, A to D converter, software based subsystem, and here you can see we have programmable devices, for example FPGA, GPP, and management software is also here. If we talk about the transmission, so digital to analog converter and radio front end, and this is the antenna. Now if we talk about USRP, that is universal software radio peripheral, so here we have radio front end, right? Radio front end, and these are the daughter boards that are actually providing this radio front end, DAC, A to D converter, FPGA, and this USRP is connected to the personal computer. So this is actually providing the interface between our analog free space and our personal computer, and here we have the antenna, right? So if we talk about USRP, right, in the context of SDR, right, so you can see we have different generations of USRP, USRP 1 and 2. Inexpensive computer hosted hardware solution for developing software radios through GNU Radio, right? So we have a open source software, and we have you can say partially open design hardware, that is USRP, in order to build the flexible radio, right? So here is the block diagram of USRP, right? So we will not go into details. So here we have the FPGA. You can see FPGA Ethernet controller, that is actually encapsulation, providing encapsulation, right? And these are the data boards receiving and transmission, right? And this actually the daughter boards, they are transceivers. Okay, so let's talk about GNU Radio, that is an open source SDR. So it support mathematical operators. We can have addition, multiplication, log. These are the operations which are very much required when we talk about the communication. Then interleavers, and we have delay blocks, filters, FIR filter, IIR filter, Hilbert filter, and we have also FFT blocks, automatic gain controllers, and GNU Radio also provides modulation and demodulation schemes. For example, FM frequency modulation, AM amplitude modulation, phase shift keying, QAM quadrature amplitude modulation, and GMSK, that is being used for cellular communication, OFDM. And then we have interpolation and decimation. It also supports certain codes, for example Viterbi, right? We can also have signal generators, noise generators, pseudo-random number generators, right? And USRP source and sink, graphical sinks. We have also oscilloscopes, audio source and sink, file source and sink, and it supports UDP also, right? So here is the picture, right? So you can see we have USRP kit 1 and 2 we can have, and here we have the interfacing via gigaspeed Ethernet interface, or we can also have USB for USRP1, and this is the C++ signal processing block over here, right? So all the modulators, all the filters, all different demodulators, encoders, decoders, they are actually written in C++, and we need some sort of sequencing and scheduling, right? So that is being provided by this framework, that is SWIG. So all the modulators, all those different functions, all those different blocks, they has to be glued together. So we actually are using Python for function binding in order to have flow graphs. So here the integration, SDR and USRP integration, so the hardware that can be used, right? So USRP and 2200, and you can use WBX daughter board for GSM quad band support, right? And we have 900 megahertz vertex antennas used for transmission and reception, and these are the softwares. GNU Radio, OpenBTS, that is an GSM stack, and asterisk. So instead of having MSC, when we talk about the GSM communication where the calls are being switched, right? So we are using a soft switch, that is asterisk. Again, it is an open source, and this is a soft switch. And then in order to support SMS service, we are using SMS queue. So here we have the front end, right, provided by those transceivers, daughter boards, and here is the hardware, that is the USRP kit or modified USRP kit. And this is the computer, and this kit is connected to computer via Ethernet, right? So if we talk about GSM and OpenBTS, right, so because as we have mentioned that this is a software that actually provides GSM access point, GSM stack, allowing standard GSM compatible mobile phones to make phone calls without depending on providers, GSM service providers, right? So functions, here we have GSM, and here OpenBTS MSC control functions, that is replaced by asterisk. Radio management, this is performed by BSC, and here we have GNU Radio, and signaling functions, they are performed by BTS, and it is being performed by USRP kit. Okay, so this is the environment. So you can see we have USRP, and this is actually the signal generator. So actually the problem with this USRP is that it don't have because it is USRP1, so it don't have exact an accurate clock that is required for GSM communication. So what we need to do over here, or what we did over here, we have dismantled its internal clock, or you can say the USRP's kit internal clock that was not accurate, and then after that we generated a signal of 52 megahertz, right, accurate signal by using this function generator, and then we have inserted this signal as a clock into this USRP kit, and in this way we have overcome the problem of clock accuracy, right. So here you can set up this environment. There are some of the issues, SIM card configuration, clocking issue as I've mentioned, and first of all we have to catch the IMSI, right. So that is international unique number, right. SIM card come with preferred network list, and to ensure the handset will scan Open BTS network, it must be set up as the first preferred network, right. So mobile subscriber identification number, so this is actually the IMSI, mobile country code, mobile network code. So first of all we have to catch up the IMSI. So how we dismantle the clock, right. So you can see we have to detach some of the components, right. So there are solutions. So this is the signal generator that has been used. Okay, so we have some of other applications of SDR. We can have AM FM radio transmission and reception. It can also be used for radar interception, spectrum analyzer, GSM interception, channel estimation, and these are the uses of USRP kit alongside SDR, right. So now the USRP's cost is very high, right. So we can have another solution that is a cheaper solution, but in that case we have certain limitations that we can only receive GSM data, so it can be receive only infrastructure. So we can use this funky dongle. So in that case we can receive the traffic only, we cannot transmit, right. So there is another $20 SDR RTL dongle, right. And so here we are going to discuss the routing and the switching that we are going to support by using our existing solution. So we have the infrastructure like this. This is, you can say, you can assume that these are different cells, very small cells, right. So we need to perform routing and switching of calls between those different small cells, very small cells, cell A, cell B, cell C. And here we have different hardware, software. You can see we OpenSIPs, that is a SIP proxy, OpenBTS, that is again GSM stack, and USRP, that is a hardware, specific hardware to support the interfacing between the environment, free space, and in order to have communication, GSM communication, right, or GSM infrastructure. And then you can see they are joined together, and here on the other side we have the fixed network, right. So now you can say that we have heterogeneous sort of infrastructure where we have fixed telephony that is being supported by using different interfaces, TDM, T1, E1, Ethernet, Wi-Fi. We have ISDN, BRI, J1, and UMTS, right. So on the other side we have a totally GSM communication infrastructure. So here all the communication, all the services, they are being provided by using GSM infrastructure. So we have to perform routing if somebody want to call from this fixed infrastructure to GSM. So there should be some mechanism to route this call, and if somebody from this GSM infrastructures want to call at some number that is associated with this fixed infrastructure, so he or she should be able to have this service, right. Okay, so here is the mechanism, and we have a policy server that is actually used in order to have certain set of policies. So we will not go into details, right? So it's the same, that all the data has to be there. For each cell we have a slave OpenSIPs, and all the data from those corresponding slave OpenSIP servers for their corresponding cells is mirrored as at master SIP, right? So it's the same sort of infrastructure where we have a BTS, and then we have BSC, and then we have BSS, and then we have main switching center, right? Okay, so the data, the request will go here, and here the policy server will be calculating the decision, and then the decision is enforced, and the call is routed to a particular link, right? So we actually have used multi-criteria decision making in order to achieve this decision making. So you can see we have user profile, link profiles, business objectives. So there's a whole bunch of data that has to be taken into account in order to compute the decision, right? And here the method topsys that is used, also you can see this is the criteria, and these are the different metrics, right? Utilization ratio, delay, jitter, packet loss, total bandwidth, available bandwidth. And if I go back, so here we have links, different links, right? So you can see that these are different links over here, L1, link 1, link 2, link 3, link 4. So the decision making matrix, right, is, and all the criterias are assigned different weights. For example, if I'm going to have a voice communication, so in that case I cannot afford jitter, right? So packet loss, okay, I will giving less weight. Jitter I cannot afford, I need reasonable bandwidth, right? So here is the results that are calculated, and then we have integrated some of the, and this is important. So if somebody is here and he's moving here, so in that case handover has to be performed. And remember, we are living in the same technology world, so we have to perform the horizontal handover in that scenario. And this is the captured traffic. When we run our communication infrastructure, you can see that we have captured the traffic, right? And this is the GSM stack, GSM tap. We can use GSM tap filter, but we need air probe, we need Wireshark, right, in order to do that. So there are a lot of other applications of OpenVTS plus GNG radio plus USRP. So we can launch, as mentioned, a solution very quickly for in case of disaster scenario, right? And we can also have, for example, if we have an earthquake or maybe a flood situation. So you know that nowadays everybody has its cell phone. So we can build a system so that by using that system we can detect that there is somebody under the debris, or maybe somebody is in demanding for some sort of help, right? And here are some of the other applications of this solution, OpenVTS plus GNG radio plus USRP, right? So we can provide cheap services. It's low cost, low power, reconfigurable, flexible communication system. We can also support GSM to voice over IP convergence. You can also have security applications, for example, jammings. So that's all for today's lecture. So today we talked about software-defined radio. We established that why we require software-defined radio. What are the motivations behind software-defined radio, right? And if we talk about software-defined radio, so it has a great potential, but its potential has not been exploited yet. There are a lot of military applications because the software-defined radio was, the idea was launched or came from military, and that's why there are a lot of military applications. But as far as the research, academia and industry is concerned, they can benefit a lot from this technology, right? So there should be a lot of civil applications. We can have a lot of different products, and we can reduce the time to market, right? So we can have a lot of different products, and we can market them effectively, efficiently and quickly. And there are a lot of different techniques, right? And that can be realized, and that can be designed and developed by using SDR. So that's all. अपना बहुत ख्याल रखिएगा. मेरी तरफ से अल्लाह हाफिज़. अस्सलाम वालेकुम.